Hi everyone. Let's talk a little bit about polar derivatives, and in particular the derivative dr d theta. So we've talked about things like dx d theta and dy d theta, finding horizontal and vertical tangents. We're thinking of polar there as a particular parameterization. But what does dr d theta mean? It turns out it has a very nice interpretation. So we can start just by thinking about some simple functions like polar functions that have polar derivative equal to 0. So what would it mean to have dr d theta equal to 0? Of course, we know that r equals c, a constant, would have a polar derivative equal to 0. So we could think about functions like r equals 2 or r equals 10, things like that. And of course, we know that those are all circles. So when we go to graph these things, we can see that r equals 2, this is a circle, and this has constant polar derivative. So what I want you to try to do is to think about things through the lens of polar coordinates. We are seeing, we're increasing theta and moving around the polar plane here, and r is constantly 2. It does not change. And so this gives us a circle. So what would it mean for a function to have a constant polar derivative, obviously other than 0? Like what would it mean for dr d theta to be 1? Well, of course the function r equals theta satisfies that, as do others. We could have r equals 3 theta, which would have a constant polar derivative of 3. What do these functions look like? So we know that r equals theta is this spiral. And as we go around, notice that r, the distance to the pole, is increasing as theta increases. And so that's really the key in thinking about what the polar derivative dr d theta is doing. It's measuring how r, the distance to the pole, is changing as theta increases. So as you move around counterclockwise, what is happening to the distance from the pole? In this case, it's increasing. Now, there's a question on the sheet that asks, what does it mean for dr d theta to be positive? And you have to be careful here because dr d theta being positive means that as theta increases, the distance to the pole, r, increases. But that's if r is positive. If r is negative, if you're moving backwards, that could actually mean that the distance to the pole is decreasing, because if r is negative, dr d theta being positive means that r will be increasing, but the negative distance will be getting smaller. So, if we look at an example, something like this, like say 2 plus cos theta, or cos x rather, and we move around, here we see like the distance to the pole is decreasing, 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 decreasing. Looks like it bottoms out here and is a minimum. Now the distance to the pole is increasing. Or if we look at another example function, something like 2 plus, let's say, sine of 2 theta, or how about sine of 4 theta, or x rather. Here we get some more interesting behavior. The distance to the pole is increasing. Now it's decreasing. It bottoms out. It's increasing, decreasing, and it bottoms out. Increasing, maxes out, decreases, bottoms out, and so on. So when you solve, say, dr d theta equals 0, you're going to find these extreme values. This is a minimum for r. This right here is a maximum for r, and so on. So dr d theta really tells you the rate of change of the distance to the pole with respect to theta. This gives you a lot of information about a function, but you do have to be careful. You have to think about what it would mean for dr d theta to be positive or negative when r is positive and r is negative.